Just want to go to my notes. Okay, so we already started with part one, whereby we discuss what an operating system is. We have more or less touched on the definition of it, and now we are embarking on the different aspects associated with the operating system, or at least the understanding of the operating system. These are things that are necessary to understand for someone to be able to design, on one hand, a good operating system, and on the other hand, to be able to select an appropriate operating system for a specific type of computer system. So these aspects include computer system organization, computer system architecture. We start with computer system organization. So before we explore the details of how computer systems operate, we need general knowledge of the structure of the computer system. Because when we say how computers operate, we mean operating system, because it's the driving engine behind the operation of the computer system. But as the sentence clearly said, we need to first understand the structure of the computer. Therefore, in this section, we look at several parts of this structure. The section is mostly concerned with computer system organization, so you can skim and skip it if you already understand the concept, as I mentioned yesterday. But nonetheless, repetition is always good. And we first start by the computer system operation. A modern general purpose computer system consists of one or more CPUs and a number of device controllers connected through a common bus that provides access to shared memory. Three major aspects are identified there. Core aspects of the computer system here. Can you mention them to me, that you can read through those lines? What according to you are the three critical aspects you cannot speak about a computer system without mentioning? Actually, I will go for four. In essence, it is the CPU, one or more CPUs, one or more. And when you have multiple CPUs, and I'm sure you learned this through CGS or any other previous module, computer architecture. So when you've got multiple CPUs, you speak about a multi-core computer. Okay. So you can't speak about a computer system without having the CPU. You also have to have memory at the end of the day. I/O peripherals, that's the third element. And the fourth one is obviously the communication interface between the CPU and memory, which is the bus. Okay. And it's called common bus because it's normally shared among the different IOs. Okay, the CPU and the device controllers, because as part of processing, the core of processing is actually the CPU. So at the core of processing, you get the CPU. 1 second. At the core of processing, you have the CPU, of course. The CPU sits at the core of processing, but every IO, input-output peripheral, also normally has its own interface controller, a device controller, basically. For example, you'd have a controller for the keyboard, you'd have the controller for the mouse, etc., which in conjunction with the CPU helps in processing data from, in the case of an input device, and from that specific input, or to that specific output in the case of an output device. That's important and basic, actually, just a reminder. So the CPU as well as the device controllers can actually execute in parallel. So there's a level of parallelism in processing between the CPU and the device controllers. And therefore, they will end up competing for memory cycles because they're executing in parallel. There's probability that they can finish executing or processing whatever task they are allocated more or less at the same time, and all attempt to access the same memory. So That competition is, we are pointing it out because the operating system is the one that manages that. To ensure orderly access to the shared memory, a memory controller synchronizes access to memory. So one way this is handled, because not all resource competition have to necessarily be handled by the operating system, which is a software. Some of them are already handled by some additional hardware that are built as part of the computer system to assist the operating system. In this case, that additional hardware that helps in accessing, managing memory access conflicts between the CPU and controllers of IOs is what is called here the memory controller. So you'd have a memory controller that will manage that. So that's a piece of hardware accompanying the action of the operating system. Okay. For a computer to start running, for instance, when it is powered up or rebooted, it needs to have an initial program to run. So the boot up program, as you know it very well, this initial program is the bootstrap program. Okay, bootstrap program. And what is its purpose? Well, first of all, it's normally a simplistic program. Why does it have to be simple? Because for two reasons, is that it shouldn't take too long, and it's just an initialization part of the operating system. All it does, it initializes all the different peripherals and so on. Typically, it is stored within the computer hardware. So in the ROM memory, or electrically erasable programmable read-only memory. So either EEPROM or ROM. Why? Why does the bootstrap program have to be stored in ROM? Because if you lose the startup program, the bootstrap program, then the computer will not start up because it won't have its different aspects initialized. So it's a very critical type of program, but it's sub-program, let me call it like that, because it forms part, actually, at the end of the day, of what we call system programs, which are part of the operating system. Okay, so its role, obviously, is to initialize all aspects of the system, from CPU registers, giving them their default values and so on, to device controllers, to memory content. The bootstrap program must know how to load the operating system and how to start executing that system. So it's the one that also loads the operating system, which means it fetches the operating system program from memory and executes it. That is how you load the operating system. So now, to accomplish this goal, the bootstrap program must locate the operating system kernel, start by the kernel part of it, and load it into memory first. So that's the first step. Once the kernel is loaded and executed, it can start providing services to the system and its users. Some services are provided outside the kernel by system programs, of course, that are loaded into memory at boot up time to become system processes. Okay, so here or system daemons, and I'll explain the daemon and the process, what's the difference. But first, let's go from program becoming a process, and a process or a daemon. Once loaded, a program becomes a process. Why do we change the naming here? Process has to do with the fact that it's running. A running program is a process, because process in essence is a set of steps executing in a particular manner, one after the other, in a particular order, one after the other. But when we say daemon is to say this is just a special type of process, but which runs in the background. And there are plenty of them in many operating systems you are familiar with, such as Windows and so on. You always get, let's say, your antivirus and all of that, those type of programs running in the background. And when you in the case of Windows, when you go to Task Manager, you see plenty of these daemons running in the background. Okay, processes are actually visible, but daemons are running in the background. Okay, so that run the entire time the kernel is running. So the kernel is the one that loads, and I mean the bootstrap loads the program in memory. Starting by the kernel. The kernel executes, and the kernel, by executing, calls the other system programs, and these system programs become processes and or daemons, and they run for the entire time the kernel is running. But when we go to specifically on a Unix platform, by the way, what is the Unix? What is Unix? Unix is a family of operating systems under which falls, it's the core. It's a system of family of operating systems, because under the Unix core, we have Linux, we have Mac OS. They're all built on top of Unix. Okay. So when we speak about Unix, we speak about a family of operating systems. Okay. In the case of a Unix, the first system process is called init, and it starts many other daemons together with it. Once this phase is complete, the system is fully booted. Okay, so the moment the init is executed, the system is fully booted, and the system waits for some event to occur. So now, remember, most computer programs run in an event-based manner. So it's the occurrence of an event that triggers a process, or I mean, an application to run on a computer system. Yeah, so a typical example, one will have to click, one will have to open Word, one will have to start typing on the keyboard. Those are event-based processes. Okay. The occurrence of an event is usually signaled by an interrupt. That's a very important word, but which shouldn't be very unfamiliar to you guys. Tell me, have you done Digital Systems 3? I mean, how many digital systems have you done so far?
Yes, we've done 3, sir.
Pardon? 3 of them?
Yes.
Yeah. So you understand when we speak about interrupt, right?
Yes.
Yeah. Okay. And the interrupt can be from a hardware, in which case it's an external interrupt. Like when I click on a mouse, that is read into the computer system as an external interrupt from hardware. Or it could be from software. When it comes to software, these are timer interrupts, for example, like a clock running in the background, and after some time, it overflows. You know, hardware may trigger an interrupt at any time by sending a signal to the CPU. That's how it does it, usually by the way of the system bus. So that way, but now, you know, from computer architecture that in terms of buses, we actually have a system bus. This is also part of revision. We've got address bus. We've got data bus. Yeah, system bus, address bus, data bus. The data bus is often where the actual data is moved on to, at least in the Harvard architecture, whereby address bus and data bus are separate. Because in von Neumann, it's the same bus being used for both. The actual data is carried through the data bus. The address bus carries the address of memory where this data is fetched from in the case of reading operation, or the address of the memory where this data must be stored at in the case of writing operation. And of course, the system bus is mostly used for control signals, such as interrupt signals, etc. So the interrupt signals are part of this, a specific case of control signals in this case. Okay, so I hope that is clear. So interruption is what will get to the CPU, and the CPU, what happens, as you learned in digital systems, when an interrupt occurs, the processor stops what it was doing, goes to do what we call handling of that interrupt, and when it's finished, it stores the position in the stack pointer of where it last executed, of what it last executed, and what, yeah, it goes and handle the interrupt and comes back so that it can carry on. It reads it from the stack and carries on from where it had left. Okay. So now the software may trigger by an interrupt by executing a special operation called a system call. Yeah. Now we're getting into operating system step by step. System call, which is also called the monitor call, is the operation, so meaning it's part of the operating system. It's one of the operations of the operating system that is normally executed through the system bus to start with, between, in this case, a hardware peripheral and the CPU to signal the presence of an interrupt. So whenever I click, for example, at the level of the operating system, that is interpreted as a system call. So a system call is issued from the from the controller mode, from the operating system to handle that interruption. Okay. When the CPU is interrupted, it stops what it is doing immediately. That's exactly what I explained earlier on. The fixed location usually contains the starting address where the service routine for the interrupt is located. The interrupt service routine executes first. Apology. And when it's done, the CPU resumes the interrupted computation. So it resumes from where it had left. And that's the role of the stack, because that is where the CPU keeps the record of the last address it was executing, so that by the time it comes back, it knows where to take it from. Make sense? Make sense? Hello?
Yes, it makes sense.
Okay. So a timeline of this operation is actually shown in figure 1.3, and let's actually look at it. First of all, 1.2, a modern computer system, as we mentioned, memory must be there, CPU must be there, of course, the bus. This is one specifically is a system bus. The other core processing units that are co-processing the CPU are actually device controllers. So when it comes to disks, you have a disk controller. When it comes to USB, you normally have a USB controller. For example, USB controller is the one that manages all the low-level MAC addresses of different USBs and so on. It behaves more like a hub, and I'm mentioning this because I'm assuming you've done some network as well. You've got when it comes to the monitor, you normally have a graphic card adapter, okay, and so on. So those are controllers, those are peripherals. That's just a basic structure of a modern computer system. But now, when it comes to the timing diagram of how interrupt timeline for a single process happens, is that let's observe this wave diagram. So what happens is that we have the CPU on one hand, we've got the IO device on the other. So for a long time, the CPU is actually, if we think about the control line between the CPU and this IO device, is normally pulled high. Normally it will be pulled high at the beginning. So we are here. The CPU line is normally pulled high as long as there's no event for it to handle. The moment there's an input-output request issued on the IO device side. By the way, the IO device side is also normally by default pulled high. When it goes low, it's a way to signal that there is a request that has been issued. And for the entire time that request is being transferred through the system bus, the IO device line, control line, will remain low, and it's pulled back high the moment the transfer is done. And few nanoseconds after, so there's a bit of time that elapses after the transfer of that control request is concluded, for the CPU to realize, oh, okay, there has been interruption. I need to store that little amount of time is for the CPU to store the address of where it was executing it, or to even finish what it was busy with, and so on, save the memory of the instruction at which it was. But immediately after that, the CPU engages in handling is pulled down while the handling of the IO request is being executed by it. So for the entire period there is shown from transfer done to the next IO request, that is the moment That's the moment where on the IO side we transferred the control signal or the request to process. The CPU doesn't often take long, so it just goes low quickly, executes the request, and back high. We're talking about CPUs that are powered with gigahertz of clock, so the execution is very fast. And when it goes back again, it awaits a new request. And when a new request comes in, the same thing happens. So you'll get longer CPU execution depending on how much or how many processes the request involves. But by now, my expectation is really for you to understand the whole flow of processes of steps and how the operating system is involved. And very important, some key words that we'll keep on using: system call, process, etc. Interrupt, bootstrap program, monitor call. These are keywords you should be getting out of this. Okay. So interrupt are an important part of computer architecture. For each computer design normally has its own interrupt mechanism, but several functions are common to all of them. The interrupt must transfer control to the appropriate interrupt service routine. The straightforward method for handling this transfer would be to invoke a generic routine to examine the interrupt information. So that means for every interrupt is associated an interrupt service routine. And each time an interrupt occurs, we call that, we do what we invoke a system call. I'm not saying we call that the routine, no, because the routine, being an event-based function, it can't be called the way you would call a normal application layer type of function. In this case, it's invoked by means of system call. Okay, as you noticed, even when you're doing microcontroller programming, you never literally called a interrupt service routine whenever you wanted to execute it. It was actually always invoked from in the background in most of cases, in this case by the system call, therefore, and it was invoked through an interrupt vector. For example, for external interrupt 0 on 8051, you had interrupt vector 0, for example, and so on. For serial communication, it was 4, and so on. Okay, that is important. The interrupt must transfer control to the appropriate interrupt service routine. The straightforward method for handling this transfer would be to invoke a generic routine to examine the interrupt information, which is what I just said. Normally, it will be the same routine that's already written to handle with all possible scenarios to handle the interrupt. The routine in turn would call the interrupt specific handler. So we have a routine that calls the handler. That's very important. The handler is the actual function where we now process the interruption. However, interrupts must be handled quickly, of course. And you even experience this, I'm sure, when you're doing digital systems 3, that you don't want to do a lot of processes in the interrupt for many reasons, because that simply means you put the entire system at halt, and you might miss on new interrupts. So all you have to do most of times in an interrupt is to acknowledge that it happened, do the bare minimum being setting up a software flag to know that interrupt is occurred, so that by the time you come back to the main process, you can execute, you can check by means of that software flag that an interrupt indeed occurred, and you can process it. So you don't want to spend long in the interrupt handling. Okay. And since only a predefined number of interrupts is possible, a table of pointers to interrupt routine can be used instead to provide the necessary speed. And when you speak about a table, that means there is allocated addresses, exactly like with the 8051. You had 0 for external interrupt 0, you had 4 for serial communication, you had 1 for timer 0, you had 2 for external interrupt 1, you had 3 for timer 1, etc. So you'd have, because it's a well-known, on every system, we have a well-known set of possible interrupt that can happen. So to make the process easy, we do some sort of lookup table. Okay, so the interrupt routine is called indirectly through the table. Yeah, lookup table, with no intermediate routine needed. So you just go to the table, we check which interrupt happened, And in that table is mapped, the vector of that interrupt is mapped to the routine that is associated with the handler function that's associated with, and that is called immediately. No intermediate process. Generally, the table of pointers is stored in low memory, the first 100 or so. Why is it stored in low memory? And this is part of, once more, of the task of the operating system in terms of memory management. It's recommended that you store, you would want to store the vector table, as we call it, in low memory so that it's quicker to fetch, because the further in memory data is, the longer it takes to fetch. Yeah. These locations hold the addresses of interrupt service routines for various devices. So it just works more like a pointer. So the lower side of the memory, the early part of the memory, is having a table, and within this table, there's a map between the vector, the interrupt service, the interrupt vector, as well as the pointer to the function. And this function I'm talking about here is the handling function. Okay. This location all the addresses of the interrupt service routine for various devices. This array or interrupt vector, as I mentioned a lot of times now, of addresses is then indexed by a unique device number, exactly like with the 8051, as I mentioned earlier on, given with the interrupt request to provide the address of the interrupt service routine. So that could be the row number in that table, and, or the column number, depending on how the table is built. When it comes to storage definitions and notations, this is a quick revision, really, but which can be tricky because a lot of people don't know about this. The basic unit of computer storage of memory is bit, and it stands for binary digits. You guys are from computer engineering, you know better. Unlike the IT people I was teaching last semester, you understand very easily this from digital systems. A bit contains one or two values, so either a 0 or a 1, as you know very well. So as we go in terms of higher units, from a bit, a group of bits form different other units of memory. There's one that we don't often speak about, and that's a nibble, which is a group of 4 bits. When we speak about a nibble, we're referring to a group of 4 bits, nibble. Then, of course, from there, you've got a byte, which is often considered like the very first unit, which is 8 bits long. And the data type associated with that is often char, which can be signed or unsigned, of course. Then, when we go higher, that we've got multiples of bytes, of which we've got a kilobyte. Kilobyte, we use KBB capital letter. And the kilo, unlike in other measurement systems where kilo normally means 10 to the power 3, when it comes to memory or storage, kilo means 2 to the power 10. Okay? Above, which is 1024 and not 1000. A lot of people make that confusion. When we go one step higher, we've got megabytes, and megabytes are the same way. So a megabyte is a kilo of a kilobyte. So that is 2 to the power 10 times 2 to the power 10 bytes, and that is basically 2 to the power 20 bytes. Okay. And of course, you can go gigabyte, which is kilo, right? So that is 2 to the power 30 bytes. And terabytes, which is 2 to the power 40 bytes, etc. So that's how, those are the units of storage, of memory storage. Very important to mention that. Okay. Petabytes, etc. Terabyte, petabyte, which is 2 to the power, 10, yeah, 2 to the power 50. Okay. Computer manufacturers often round off these numbers. Sometimes they'll use the normal measurement system to do approximations on this by saying it's roughly a kilobyte is roughly 1,000 bytes, but that's not how it is. It is exactly 2 to the power 10 and not 1,000. Okay, so here you hear about 1,000,000 bytes, a billion bytes for a gigabyte, but it's slightly higher than that. Networking measurements are an exception to this general rule. They are given in bits. Most of the times when we speak about networking, we use bits because network move data a bit at a time. Most of network transmissions of data is done serially, so 1 bit at a time. Hence, when we start speaking network-wise, we often tend to use bits and multiples of bits, meaning kilobits, megabits, and so on. And you must be careful here. When it comes to bits, we don't apply the rule of saying kilo is 2 to the power 10. When it comes to bit, we are actually back to the original concept of a kilo. So when we say 1 kilobits per second, for example, is a transmission speed, that is exactly 1,000 bits per second. So when it comes to bits, we don't. It's not 2 to the power 10. It's actually 10 to the power 3, 10 to the power 6, etc. That's very important, and that was more of a revision. Now, operating systems is different as Windows and Unix dispatch interrupts in this manner. And which manner are we talking about? We're talking about the dispatching of interrupt given an interrupt request to provide the address of the interrupt service routine. So by means of the table, an array table that we call interrupt vector. So that's the manner in which we're talking about. So it's the most common approach used by the most popular 2 operating system families, which are Windows as well as Unix. The interrupt architecture must also save the address of the interrupted instruction, but that I've mentioned already, so that when we come back, we take it from it. We go to the next address after that, so that the process can carry on. The previous process we had left to go and handle the interruption. But many old designs simply store the interrupt address in a fixed location or in a location indexed by the device number. More recent architectures store the return address on the system stack. That's the modern way of doing it. If the interrupt routine needs to modify the processor state, for instance, by modifying register values, it must explicitly save the current state, then restore that state before returning. Yeah, so we just don't store the address of the execution at which we were interrupted. The instruction that was executing when we were interrupted, we often also have to store the state of the computer itself. Maybe was it idle at that moment? Was it in sleep mode? Was it hibernating and all of that? So that when we handle the interruption, we are able to return it to that state as well. Okay. Yeah. So now storage structures, because as we mentioned, you can't speak about a computer system without speaking about the CPU, memory, of course, and this is what has to do with storage structure. How is data stored in a computer? And of course, the system bus as well as the IOs. But here we're talking about storage structures now. The CPU can load instructions only from memory, of course. So it's important to point out here that within a computer system, the CPU does not store anything. It's just an executing unit or processing unit. So both instructions, meaning programs, are stored in memory, and data. By data, we mean the data on which the instructions are executed. They are both stored in memory. So the CPU therefore loads instructions only from memory. So any program to run must be stored first, of course. General purpose computers run most of their programs from writable memory called the main memory, also known as random access memory or RAM. So when it comes to general purpose computers, most of the programs is executed or run from RAM, but it doesn't stay in RAM, because if it was to stay in RAM, that would mean that when power is removed from the computer, the program will be lost. It runs it through RAM. So the CPU fetches the instructions from ROM and loads it in RAM and executes it from RAM. which is often known as main memory for that reason. Main memory commonly is implemented in a semiconductor technology called the dynamic random access memory. So it's mostly DRAM that is used in most computer systems. Unlike SRAM, which is static, DRAM is mostly based or built upon active components, which are in this case MOSFETs. Computers use other forms of memory as well. We have already mentioned read-only memory, ROM, EEPROM, of course, because ROM cannot be changed and it's loaded once and that's it. Only static programs will be stored in ROM. And these include basically your bootstrap program. You want things such as the bootloader, as we often call it in common language in Windows, to be stored on ROM because it doesn't change. It's the type of program that are written to stay. But on the EEPROM, you would store the other type of programs that can be erased electrically, of course. Although it's also important to mention that there is a maximum number of cycles you can write and read to an EEPROM before it starts. Sorry, so that's flash. Sorry, EEPROM you can write indefinitely. Pardon. If it was flash, which was the previous version of EEPROM, you wouldn't write indefinitely. There's a maximum number of cycles after which you can't write and erase anymore. For example, smartphones have EEPROM to store their factory installed programs. Remember, in the case of mobile computer systems, we say beside operating system and application programs and system programs, we normally have what we call the middleware, and the middleware is what stores all the additional it's the programs that are there to assist with provide additional support to any running application layer programs. So on a mobile phone, you'd want to have an EEPROM whereby you store what we call the factory installed programs. So these are programs that come inherently with the phone, the basic programs as we call them. And that is why whenever you're trying to delete certain programs that's on an Android phone, you can't. You can delete your WhatsApp and put it back, but you wouldn't, for example, delete your mail, the original mail app that is comes with the cell phone, because that one is part of the factory installed program. The only way to delete it is actually to erase the EEPROM of the cell phone. Okay. So all forms of memory provide an array of bytes at the end of the day. So when we speak about memory in general, as I mentioned to you earlier on, you must think of an array or a table. So whenever you speak about memory, you think of an array or a table. The addresses are row numbers, and the columns is where the data is actually stored. The simplest unit of memory is what we call a memory cell. On small computer systems like the AT51, the memory cell has got a size of 1 bit. But in general, with personal computers, mobile cell phones, and other higher computing devices in general, every cell corresponds to 1 byte. Okay. So these are addresses. The size of data contained in one specific address, let's say address 0, which in hexadecimal is 0000, for example. The size of one full address, meaning that, all of that, which is actually equal to the number of columns times the size of one cell, which could be 1 byte, which is 8 bit. That total size is what we call the word length. The word length, which simply means it's the basic unit of memory that can be accessed by a specific computer system or CPU. So that is what you can manipulate. On a AT51, it's an 8-bit microcontroller. What that means is it simply that its word length is 8 bits. So you can manipulate a bit at a time. Whenever you want to manipulate lower than that, you do that through some software manipulations. Okay, that's important. A typical, so that was important to mention about the factory installed programs, and now we're talking about the structure of memory. So each byte has its own address, so that takes us back to a cell being 1 bit actually, sorry. Number of columns. So in most cases that will be 8 bits in total. Okay, but we do get 32-bit microcontrollers, for example, whereby the word length is 32, so it's 32 bits for one word length, and you get more 64-bit microcontrollers, etc. Okay, each byte has its own address. So as I mentioned, the addresses are rows. Okay, interaction is achieved through a sequence of load and store instructions to specific memory addresses. So the loading instruction is what we call the read instruction. At the end of the day, it's about reading from memory. The store instruction is about saving to memory or write instruction. The load instruction moves a byte or word that we call word length from main memory to an internal register within the CPU. Whereas, so we read from memory to CPU and within a register of the CPU, of course. Whereas the store instruction moves the content of the register to main memory. So we take, when it comes to storing, let's say after an addition, we want to store the result. The result will appear, let's say, in the accumulator, which is one of the special function registers of the CPU. Now we need to move it from there to an actual memory address, and that is the store instruction. Okay. Aside from explicit loads and stores, the CPU automatically loads instruction from main memory for execution. So some instructions are loaded automatically from main memory, meaning from RAM for execution. Okay, so not all, so some data and some instructions are loaded from directly from the main memory or RAM. Others are loaded from the ROM memory. In this case, an EEPROM, for example, in case of a mobile operating system, if it's factory programs, you load them from EEPROM, but in general, that will be loaded from ROM. Okay, that is very important. Then we have the two architectures, because the loading and the storing, of course, I've explained it already. Process, I've explained them already. The CPU puts the address on the address bus in the case of loading, and the control units and the memory controller. The memory controller, which is made of a memory decoder, gets the address through the address bus, decodes it, and then identifies the specific row we are trying to read from. Then it goes there and loads the data from there and pass that data onto the data bus this time, and from the data bus through the control, through the system bus, the control unit is notified of data coming, and the CPU then takes the data from the data bus. That's how a load instruction will happen. For writing, the same things happen. The CPU loads data from its register to the data bus, as well. Not only the data, it also loads the address of where it wants to write that data, and through its control unit it sends the signal for writing, and the signal for writing is received by the memory decoder, is decoded. It decodes the address where we want to write it and takes data from the data bus and writes it in that specific address. But that's basic, and you've studied that already in digital systems to a certain extent. So you understand that we have what we call an execution cycle, which is made up of fetch, a couple of instructions, one of them being the fetch instruction and the other one the store instruction. So now fetch and store. fetch instructions from memory and storing instructions to memory in some conditions. So now we have different architectures, and we have a specific dedicated section for computer architecture, but we have different architectures, but there are two major ones. We've got a von Neumann architecture in which the data bus and the address bus are shared. So if you have to store data, you would send one at a time. You send the address first, then the data after on the same bus. But we also have Harvard architecture, whereby you have separate data bus and separate address bus. So you would send both data and address more or less at the same time, improving therefore the processing efficiency. Okay. So we have what we call an instruction register on the CPU side, which is where instructions are loaded. The instruction is then decoded and may cause operand to be fetched from memory and stored in some internal register. If the instruction involves some data, for example, that need to be fetched from memory, that data might have to be fetched from memory through the address and data bus once more, and the instruction that was fetched before the data is then going to use that data to execute. Let's say addition between two numbers, one being fetched from memory, one maybe being obtained from an IO device, like a keypad or so. Okay, so that's a typical basic operation of a computer system in terms of its computer system organization. Okay, so that is very important and well known. We go to the next section. Ideally, paragraph. Ideally, we want the programs and data to reside in main memory permanently. This arrangement usually is not possible for the following reasons. Main memory is usually too small to store both data and address. So all needed programs, which is programs and data, all needed programs and the data permanently. So most of times we have also the fact that main memory is volatile storage device, meaning it loses its content when power is turned off and otherwise lost. So main memory here, it's RAM. We're talking about when we speak about memory. Main memory is volatile, meaning it's RAM, not ROM. Thus, most computer systems provide secondary storage as an extension of main memory. So you'd have some form of extension of main memory. The main requirement for this secondary storage is that it should be able to hold large quantities of data permanently. That is where you have your EEPROMs, for example, on top of the ROM and the RAM within a 8051, for example. You might need to have an external EEPROM, for example. Okay. The common secondary storage type is the magnetic disk. On a computer system, mostly we have disks. On a microcontroller system, you might have an external flash. Memory card, you might have an external EEPROM. Okay, but when it comes to computer systems like your personal computers, your servers, your mainframes, we often refer to these extra memories as disks. They provide storage for both programs and data. Okay, that's important. So the wide variety of storage systems can be organized in a hierarchy. There's a hierarchy in which the different storage systems can be organized according to the speed as well as the cost. Obviously, speed, the lower level is where we can easily fetch from. The deeper levels take longer to fetch from, and cost, of course, has to do with every extra memory you add, such as RAM, extra RAM, comes with a cost. The higher levels are expensive in terms of speed costs already, meaning fetching cycles, but they are fast. The higher levels will be expensive in terms of money-wise, but they are fast. That's the benefit they have. And let's look at them. When we speak about the higher levels, we're talking about the registers. Wait a second. No, we're talking about magnetic tapes. It goes, the very closer ones are lower levels. They're easy to fetch from. The higher levels are the magnetic tapes, the one right at the bottom. Your optical disk comes next, the magnetic disk, the solid state disk. No, let me think. Sorry, apology. The magnetic tapes are the cheapest type of memory. Yeah. Then optical disks, meaning they are read by an optical eye, meaning an infrared of some sort, come next. But they are hardly not. Those will be your CDs, etc. But most computers use magnetic disk, most. But now more and more there are computers using solid state memory, SSD, as we call solid state disk, because they don't turn and all of that, but they are built from more or less flash memory, so that's why they're expensive. So as you go from lower side to higher side, you get more and more expensive. Of course, more RAM costs more cache memory costs a bit more, and registers, adding registers to computers, that's why we don't even add registers to computers, will cost even more. Okay, but already from common computers normally use that. Older computers use this too, and more and more modern computers are using solid state disk. And of course, we still have those basic amount of those in every computer system: registers, cache, and main memory. But most of times, it's not things we upgrade, at least on a personal computer, but it's things you can upgrade on a server type of computer system. Okay, so as you go from bottom to high, you increase cost, but you also become faster. Yeah, that is exactly what is explained there. But let's look at when external power is restored, the controller copies the data back into RAM. Okay. The controller has to reload RAM because RAM will lose the data if power was off. Another form of solid state disk is what we call the flash memory, and I've mentioned it many times, which is popular in a lot of things: cameras, PDAs, personal digital assistants, meaning tablets, etc., robots, which is a microcontroller system most of times. Increasingly, for storage of general purpose computers as well, you can have some flash. Flash memory is slower than dynamic RAM, of course, but needs no power to retain its content. So it's a permanent memory storage. It's non-volatile. But we also have another form of non-volatile storage, which is called NVRAM, and that is non-volatile RAM, which is DRAM, but DRAM with battery backup power. Sometimes you have DRAM. The battery backup power can be something as small as a supercap. And I'm mentioning supercapacitors because you guys have done electronics as well. So supercap is the cap that is capable to retain some voltage even when power is off. Okay. The design of a complete memory system must balance all the factors just discussed, meaning speed, cost, all of that must be balanced. It must use only as much expensive memory as necessary, while providing as much inexpensive non-volatile memory as possible. That's a good way to summarize it. Caches can be installed to improve performance, and this is mostly on servers that we go and add caches because they are expensive. And to improve performance when a large disparity in access time or transfer rate exists between two components. Yeah, that's why it's more appropriate for servers, because in the case of servers, it's multi-use and workstations are trying to access the server. So you can add more cache to improve the transfer rate or the access of workstations to the server, for example. I think we'll stop here today. We'll look at I/O structures next time. Unless there are any questions, that's it for today. I only had one person attending, which is bad, but I will speak to the others in the group. Okay, Rambuda, thanks for attending.